Hello there. My name is Jeremy Cowan. I'm a Specialist Solutions Architect for Containers, and with me today is Justin Pirtle, a Specialist Solutions Architect for Serverless Technologies. And today we're here to talk to you about the power of and, leveraging Lambda and containers in modern applications. We're going to begin by talking about the evolution of computing. Next, we'll share with you several different architectural patterns where we see these technologies being used. We'll give you several considerations for leveraging containers and Lambda in your applications, along with a decision tree to help you decide which is appropriate for your application, or which combination of those is appropriate. And then finally, we'll give you a couple of examples of where you can use both of these compute types in your different workloads.
We'll start with the evolution of computing. Now, over the course of the last decade, we've seen an evolution that began with the deployment of physical machines in an on-premises data center. The innovation factor here was relatively low, capital investment was rather extensive, and the physical machines persisted on-premises for a relatively long time. Then we had the introduction of virtual machines, which gave us greater hardware independence. Organizations that were harnessing the cloud were able to trade that capital expense for an operational expense, and they were able to achieve faster speed and agility and reduced maintenance. Eventually, Docker gave rise to the popularity of containers. And organizations were able to achieve platform independence. They were able to bin pack a lot of containers onto the instances that they used to achieve greater utilization. And containers allowed them to start their applications faster, literally within seconds. And now we have environments where the cloud operator like AWS is able to offer fully managed compute, things like Lambda and Fargate, which gives us things like continuous scaling, built-in fault tolerance, and the ability to pay for value with no maintenance required on behalf of the customer. Now I will transition to Justin to talk about the evolution of architectural patterns.
Thanks, Jeremy. So in conjunction with the evolution of computing that we've observed, we've also seen a move and an evolution of architectural patterns. And in particular, we've seen a move with customers in the industry from monolithic applications to microservice-based applications. In a monolithic application, a single deployment does everything, which means as you need to scale out pieces of functionality, you generally need to release and scale the entirety of the application, which creates rigidity in your scaling. This means it's harder to release new changes because you have to stabilize a build, and it's harder to rapidly iterate and adopt new technologies. With microservices architectures, you have different services which are smaller in scope and do a single thing or single purpose responsibility services that allow you to deploy each of them independently and scale them independently, meaning that a smaller change can be released rapidly, and it even allows different teams to use different technologies. Now, the reason that we've seen this rise in popularity so much is ultimately customers want to grow their business, grow their market share, grow their revenue, which means they need to build better products, innovate faster, releasing faster, and then ultimately focus on their key business logic and not so much on the underlying operations by being able to decouple their systems and release faster. And so this has led to the rise of serverless computing. And whenever we use serverless, it means many things in the industry, but here at AWS, when we say serverless, what that means is fundamentally that there's no instances to manage, no infrastructure to provision. You pay for what you value, in the sense you're only paying if your function is running or if something's actually doing something of use to you. The services automatically scale and are fully managed, and of course, high availability and security are built in. So serverless really is different categories of services. I mentioned it started with Lambda, but we have services that relate to serverless integration. So these include services such as API Gateway or AppSync, which can be a front-end component and API layer for something that's a GraphQL or RESTful API, or even a real-time WebSockets API. Additionally, we have Simple Queue Service, SQS, Simple Notification Service, SNS, and Step Functions that all relate to asynchronous processing and distributed sort of orchestration of your applications. So whether that be queuing, subtopics, or just broader distributed workflows, all three are there. Additionally, we have serverless data stores. So this includes Simple Storage Service, or S3, for object storage, Amazon Aurora Serverless for a relational database service, and then Amazon DynamoDB for a document and NoSQL database in a completely serverless manner. And then finally, we have serverless compute. So for today's discussion, we're really focused on AWS Lambda and AWS Fargate. And when you compare these two, AWS Lambda is a serverless functions service. So the key thing here is it's event-driven, allowing you to use different runtimes to run your code, your function, and natively integrate with different data sources in a fully managed way. When you compare that with AWS Fargate, we have a serverless container service where you have the ability to run long-running container-based jobs that abstract away the platform and fully manage the orchestration of the cluster underlying the containers and fully manage any scaling operations of that cluster. So you just focus on the containers you want to run and how you want to scale your containerized service. So let's first dig in and take a look at AWS Lambda. So AWS Lambda, as we mentioned, is a serverless functions service. So your function is your code, and it can be written in a variety of runtimes. And along with AWS Lambda and your function, you also have different event sources. So the event source could be a change in the data state of something, like, for example, a DynamoDB table, where you've maybe written an item to the table, and now we've actually changed that state. So we're going to stream the change in the state off, and Lambda will pick up that change and then be able to replicate the change or log the change somewhere. Or we could have a request to an endpoint. So if you're putting API Gateway or AWS AppSync in front of AWS Lambda, any invocation request to your API layer could trigger your serverless functions behind the scenes, which can then go ahead and as it's your code, could talk to anything that your function can do and talk to on the internet or any other AWS service. So the way this works is the function is given effectively an AWS security role and context that allow it to talk to anything in AWS as well as get out to the internet if you allow it to. And then finally, you could have other changes in resource state that are being event-driven in nature and triggering your function as those happen. Now, your function itself can have runtimes beyond the ones listed. So we do offer the ability now to bring your own runtime, which is available as of November 2018. And now, even if the managed runtimes that Lambda comes with out of the box don't include the runtime of your preference, you could bring your own runtime to the Lambda environment. And when you look at a Lambda function, it has several key pieces. It has a handler, which is where we enter your code. And that handler function receives two objects. It has an event object and a context object. And so the event object is whatever the data is coming in from the invocation, or the event source in this case. So if you're reading something like an SQSQ, the event object would have a particular schema according to what a message looks like coming from SQS. Or if you're getting an event from an API, the event object is going to be the structure of your API model being sent in as the payload of the API call. And then the context object is there as well, which are methods available to interact with the runtime. So you have a variety of different options in here, including log groups, request IDs, etc. So with Lambda, now that you understand what Lambda is there for, we see Lambda used in a variety of use cases out there. And many customers find it easiest to start with using Lambda for IT automation. So these include things such as perhaps turning off the dev environment at 7 p.m. each day and turning it on again at 7 a.m. So schedule tasks, for example, where Lambda could go out, look for anything tagged environment equals dev and suspend that instance. It could be used to orchestrate account setup and ensuring everything is set up to the right compliance and governance standards of your organization. But we see customers eventually move beyond IT automation and look at things such as data processing. So in the data processing world, whether it's processing messages that have come through pub/sub architecture with simple notification service, or queue-based processing with simple queue service, or SQS, or stream-based processing with Kinesis data streams. All of those natively integrate with Lambda, where Lambda function doesn't worry about how to read the event source, it just focuses on how to handle the processing. And then beyond that, we see customers go and actually build entirely backends with serverless applications in Lambda. So this is where we could have API gateway paired with a Lambda function to build a mobile backend or a web application backend for various apps and services, not to mention AWS IoT integrating natively with Lambda. And then the web applications themselves could be hosted and powered by Lambda. And then finally, Lambda has many other use cases, but just some of these include Amazon Alexa skills, chatbots integrated with Amazon Lex, and others. Now I'll turn it back to Jeremy to talk to you more about the container ecosystem.
Thanks, Justin. So you have a couple of options when it comes to orchestration. You can use ECS, or the Elastic Container Service, which is a orchestration service that we developed and released in 2015. Or you can use EKS, or the Elastic Kubernetes Service, which is an open source, very popular open source project for managing containers. You can choose to run those containers on EC2 instances, or as a serverless container with AWS Fargate. And we also have an image registry that you can use to store your container images, called ECR. Now, when you choose to use ECS and run your containers on an EC2 instance, you have to manage the collection of instances that are a part of your cluster. The control plane, which is comprised of various components, including the cluster manager, which is responsible for maintaining the state of the cluster, along with the placement engine, or scheduler, which is responsible for scheduling or identifying the instances that are eligible to run your containers, and then scheduling those containers onto those instances. That is part of the managed service, right? When you use Fargate, you no longer have to manage those EC2 instances, which could involve like patching and updating those instances, scaling those instances periodically for times when your services need to scale. All of that management and overhead is done for you by AWS. And ECS, the orchestrator, has been integrated with other AWS services, including things like VPC networking, where your task can actually acquire a VPC, an IP address from the VPC. It can receive traffic from all the different load balancers that are available within AWS. You have the ability to assign IAM roles or permissions to tasks, which allow them to call other AWS service APIs. And it's integrated with CloudWatch for both monitoring and metrics, and a whole host of other services, things like parameter store for storing environment variables that can be fetched at runtime, or secrets manager for fetching sensitive material that could be used to access a downstream system. The emphasis here is that we've done a lot of work to integrate ECS with other AWS services to provide a seamless experience. With EKS, we offer a similar type of management as we do for ECS, in that we're responsible for the control plane. The Kubernetes control plane consists of various components, including the API server, the controller manager, the cloud controller, the scheduler, along with the etcd database. It is a highly available dedicated control plane for each cluster. The worker nodes themselves, like ECS, are managed by you, the customer. But in the near future, Fargate will be available as an option. So if you choose to use that, you'll no longer have to manage the individual worker nodes. As for the different use cases, they're actually very similar to Lambda. Now, there are a lot fewer triggers available for ECS, but nonetheless, you can use or you can run an ECS task in response to an event like a CloudWatch event. You also have the option of scheduling recurring tasks. But oftentimes we see folks get started with containers by using them for things like APIs or web front ends. That evolves into like backends for mobile applications or running batch processing, including real-time batch processing, where you might be ingesting a stream of video, converting that into a dot cloud, and re-rendering that video in 3 dimensions. AI/ML is also becoming an extremely popular workload for containers. A lot of the organizations in the autonomous vehicle industry are beginning to use containers for vehicle training. We also see containers being used for things like build jobs, particularly with Jenkins. And client-side load testing is also another really popular option, especially with Fargate, because it allows you to quickly provision a set of tasks that can apply a load to an application, and then once those tasks are done, they're deprovisioned. You no longer have to pay for that capacity. And then finally, containers are a popular way for organizations to transition to the cloud. A lot of them have begun to containerize their legacy applications. These are typically monolithic applications, and then run them using either EKS or ECS, and then over time decompose those applications into microservices. All right, on to architectural considerations.
Thanks, Jeremy. So when we look at these services and when to choose one or the other or both, one of the first important things to understand is the shared responsibility model that AWS follows and has with our customers. And so the key thing to understand is the different levels of abstraction. So at the lowest layer, when you look at a service like Elastic Compute Cloud or EC2, in this case, AWS is responsible for the physical hardware, the software of the hypervisor, the networking, and the facilities management. But everything above that, what you do with your instance, is all the responsibility of the customer. So what are you using as the OS image? What are you putting in the application code? How are you interacting with data sources and scaling your service? And in particular, how are you creating your configuration of your security and your network configuration, and how are you basically patching your services over time? So as AWS, our level of visibility and purview goes up to the hypervisor, but we can't help beyond that with those other tasks with EC2. But when we look at higher level services and containerized services such as ECS or EKS, in this case, not only does AWS manage the same things as EC2, but we also manage the container orchestration control plane. So at this point, all you're responsible for managing as a customer is your application's code, the data source integrations, what is in the actual container, and the task definition effectively and service definition of your containers. You don't need to worry about the control plane and the state management and other areas there. But you still do need to be conscious of the configuration that you're setting for network configuration, firewall rules, how you're applying updates to your container images, etc. Now, when we look at a serverless service, so for containers, this being AWS Fargate, in this case, it's not just the control plane that AWS is managing for you. We're managing the underlying container cluster. So the container cluster is abstracted away. You don't have to worry about having capacity there. You just worry about setting your service scaling policies appropriate for whatever your service does, and the actual cluster scaling and the control plane and everything else that we mentioned so far regarding the hardware, the hypervisor, the container runtime, etc., all managed by AWS. So here you focus on your container code, your application code, the data source integrations, but you still have the power to configure the security configuration and network configuration appropriate for your container tasks and services. And then finally, with something like AWS Lambda as a service for serverless functions, the most abstracted service in this stack. This is where AWS manages even more. So now we're not just managing the cluster level scaling and the cluster orchestration, we're also managing an application level runtime for you, including updates to that runtime. So in this case, all you have to manage is your application code and set your network firewall configurations, IAM roles and policies appropriately. But even the data source integrations, Lambda will natively do for you. So for example, if you're having a Lambda function read a queue, the Lambda service includes a polling capability to check that queue for messages. And when and only when there's a message in the queue will the Lambda service invoke your code in your function. And it will invoke your code with just the messages in the queue. You don't have to build a polling capability into your code. The data source integrations are native to Lambda. And this being the case for streams, for queues, and for other integrations across the ecosystem, such as the backends to APIs, etc. So with that said, we'd like to next take you into a deeper look at each of these services in a variety of focus areas and functional areas. And we'll go ahead and start out with just the development experience, starting with containers.
Yeah, when it comes to authoring containers, the first thing that you need to do is to create a Docker file. A Docker file contains a set of declarations that are used to create a container image. Depending on the language or runtime that you use, you may use a multi-stage build, where in the first step, you're actually compiling a binary, and then in the second step, you're copying that binary into a container image that runs the application. As for testing and debugging, you can do a lot of testing and debugging in the absence of these other options I'm about to tell you about. Docker Compose gives you the ability to run multiple containers together, but there are times when you would like or need to mimic certain behaviors that are only available within the cloud. And so these local containers for ECS give the ability to mimic things like EC2 metadata and task metadata, so that when you move that application from your local machine to a production environment like ECS, you know what to expect. For EKS, you have a lot of options. You can use tools like Scaffold and Draft, which give you the ability to write your application, and then from that application create an image that can run on a Kubernetes cluster. You can also run that, or have that Kubernetes cluster running locally on your machine using projects like Minikube or Micro K8s.
So with AWS Lambda, the authoring experience is a little bit different. The first thing to understand, because Lambda is your code and your function, is what does your function need to do? And what is the event source for that function going to be? So you want to map out the broader event source architecture and know if you're reading an SQS there's a certain event structure you would expect for an SQS message coming into Lambda. And ideally, you go ahead and write your function code, and you organize your code where only the handler function needs to understand that, the syntax or the schema of an SQS event, and then could ultimately use internal helper functions to really have your business logic separated from your handler. Now, once you have your code written, most times you're going to have dependencies with your code that are important for it to run effectively. And you're going to want to ultimately compile the code if you're using a compiled language. And then once you have the compiled code or scripted code, if it didn't need a compiled language at all, You want to bundle the dependencies and the code itself into a zip file. And then once you've uploaded the zip file, then you can either create or update the function to use the latest code. Now, for testing purposes and debugging purposes, we have several tools available that make this easier to locally test and locally debug. And so we have the SAM CLI and the Amplify CLI that allow local mocking and test invocations of Lambda. And we also have, with the SAM CLI, the ability to even locally emulate API Gateway as an endpoint and the Lambda service all up, which you can directly locally test on and with before you ever upload your code to the Lambda service. But once you have your authoring and testing locally complete, the next thing you want to look at is how are you going to package and deploy this code. And so we'll take first a look at containers.
So when it comes to packaging containers, like I mentioned on the previous slide, the first thing that you want to do is create a Docker file, and from that create a Docker image. That image is often pushed to a private registry like ECR, but could also be pushed to a public registry, for example, Quay or Docker Hub. And there are several different tools available for you to build these images. You can build them locally on your laptop using Docker and then push them to a registry like ECR. But the more prevalent options include things like Code Build, which is a managed build service from AWS that not only will create compiled assets for you, but it will also has the ability to create images that can then be pushed to ECR. Jenkins offers similar functionality, only as a self-managed service. And then Helm is a package manager for EKS, and you have the option, particularly if your application is complex and requires multiple Kubernetes objects to be deployed. Helm is a very convenient way to package and deploy applications of that type onto Kubernetes. From a deployment standpoint, for ECS, the first thing that you would do is create a task definition and then a service definition from that task definition. That in and of itself will trigger a deployment of the task that you specified in your service definition. With EKS, it's a little different. You would start by creating a deployment that will deploy your pods onto the cluster, and then if you want to expose that deployment either internally or externally, you would create a service for that. The tooling for deploying your application is very broad. You could use things like Terraform and CloudFormation or the AWS CDK, the Cloud Development Kit for ECS and Fargate. You can also use Code Pipeline to orchestrate that deployment. While you can use those for Kubernetes, it's less prevalent. Oftentimes we see folks use Jenkins for both build and deploys, or perhaps Jenkins for the builds, and Spinnaker, which is an open source project that was started by Netflix for deploying applications onto Kubernetes.
So next we'll take a look at AWS Lambda. So when it comes to packaging, as we mentioned, it's your code and your function. So you need a way to compile your code, compress your code with any dependencies all into a single zip file. Well, you don't have to do this manually, though you can. Instead, there's a variety of first-party and third-party tooling available. And so first-party tools available from AWS include the Serverless Application Model, or SAM for short, which is a tool to be sort of a shorthand on CloudFormation with a CLI to allow local development and testing. And so the SAM CLI itself will actually package all this for you, upload it to S3, take care of that for you. Additionally, we have the Amplify toolchain and CLI, which can do the same. And we have the Chalice tool, which also has a CLI, which is for Python-based applications, for mainly web applications or web APIs with Python. And then we have something called the Cloud Development Kit from AWS, as Jeremy mentioned. And so Cloud Development Kit is designed for those that prefer sort of imperative programming built on top of CloudFormation. So effectively, you write imperative code that compiles down to a CloudFormation template, and ultimately CloudFormation is what orchestrates the deployment. Now next, we'll take a look here at deployment, and so we can see here that on the deployment side, you have to first have your code inside an S3 bucket, or you can upload it with the console, which behind the scenes puts it in a bucket. And then once that's there, you can create or update your function referencing the zip file and the code within the zip file. You have the ability to use aliases to enable different code versions, immutable versions of the same function to be there at the same time, and quickly traffic shift instantly between one to another. And so we have a variety of tools here, first-party tools as well, to help with the deployment. So as I already mentioned, the serverless application model, or SAM CLI, Amplify CLI, Chalice, the CDK, Cloud Development Kit, and CloudFormation, ultimately being the orchestrator behind most of those to actually make the function changes go into production. Now these are examples of all the first-party tools. We also have a variety of third-party tools available in the ecosystem for serverless. And at the end of the day, you could build even your own third-party tool given just the APIs available from AWS and the AWS SDKs. So what matters here is not so much which tool you use, but that you have an automation strategy for packaging, deploying, and getting your code to production in a rapid manner that automates this away and reduces any manual intervention and perhaps manual error that could come with it. So the next area, once your code is in production, we want to focus and take a look at how we would monitor and operate it.
So when it comes to operating a containerized environment, there are a variety of things that you need to consider. The first is around logging, how you're going to capture logs from your application that's running inside these containers. And here there are various options available, from CloudWatch logs, which is a log driver for Docker, as is FluentD, which you can use to capture not only the Docker logs, but also application logs that don't necessarily write to standard out or standard error. And then there are plenty of third-party options that you can use, things like FileBeat. For metrics, we recently released a new adjunct to CloudWatch called CloudWatch Container Insights, specifically designed around monitoring containers that run on ECS and EKS. Down below, you're actually seeing a screenshot of the sort of metrics that you can get from Container Insights, like memory utilization, CPU utilization, and others. A very popular option for monitoring a Kubernetes cluster, an EKS cluster specifically, are things like Prometheus and Grafana. And then finally, for tracing information, you can use things like AWS X-Ray, or for Kubernetes, you can use things like Jaeger or Kiali. Jaeger is a distributed tracing solution that's primarily associated with Kubernetes, and Kiali is a way to visualize a lot of the information that is gathered from not only Jaeger, but also Istio, which is a service mesh that is available for Kubernetes. X-Ray can work across both orchestrators, both ECS and Kubernetes, and provides very similar distributed tracing information as Jaeger.
So when it comes to Lambda, as a first-party serverless function service, there's native integration with CloudWatch. So from a logging perspective, anything you have your function write to std out or std error ends up in CloudWatch logs each time the function runs. And then for the Lambda service itself, both across the service and per function, there's a variety of key metrics that you can track an alarm on, including errors or throttles or any of those things, as well as a variety of automatic and configurable sort of retry mechanisms that you could take advantage of, including writing to dead letter queues, for example, in the event of an invocation not succeeding. So to keep track of what's going on in such a distributed architecture, it becomes really important to have more than just the logging and the metrics, but to also have tracing. So you can see a given interaction, a given customer experience flowing end to end through your architecture. And this is where we have the service AWS X-Ray, which is a distributed tracing service. It's not just for Lambda, it's also for containers, as Jeremy mentioned. But what I've shown here in this screenshot is an example of a Lambda function being invoked related to an S3 bucket. And in this case, it actually shows you the function's performance when the function entered initialization, the fact that it actually tried to make a call out to the S3 service, but ultimately received a 404 response in this particular case, showing that the object wasn't there. And this is just an example of digging into a given service trace, so looking at the segment there of all of the activities going on. But more broadly, you can see across your entire services, across all microservices, what is the health and the performance like end to end for customers. And only dig in when there is something of concern here, either latency or error concern or whatever it may be. X-Ray lets you figure out the root cause more quickly. So even though these are all first-party services, should you decide to have third-party monitoring, logging, or other tools in place, most all of these have native integrations that the third party can pull the logs. You could either ship the logs to a centralized Elasticsearch cluster on AWS, or the third parties could pull them from CloudWatch, including your metrics. So there are many other options here as well if you include third-party tools. So now that we have things in production, a key focus area that comes up for customers that we wanted to address was the scalability and reliability behaviors of these services.
So when it comes to containers, there are two dimensions to scaling. There's the cluster scaling, where you're actually adding instances to your cluster, and then there's service scaling for times when your application needs to scale. And coordinating between the two can be challenging. You have to ensure that there is enough capacity within your cluster for your services to scale. And then similarly, when you scale in, you don't want to target instances that are running a lot of containers, because then those containers will have to get rescheduled, and that could potentially cause a disruption. So coordinating the scaling between those two is really important. For Fargate, you don't have to worry about that because AWS will automatically scale the underlying infrastructure for times when your application needs to scale. And to do this, you would create a scaling policy similar to what you would do if you wanted to scale the number of EC2 instances that you had running. You create a similar type of policy, but you apply it to an ECS service. And from a reliability standpoint, there are a couple of ways to verify the health of your applications on ECS. For example, you can use the integrated health checks that our load balancers have, or you can use the built-in Docker health checks. With ECAS, you have similar options. They're known as liveliness and readiness probes, and they're there to really validate that your application is healthy and running and is able to receive requests.
On the Lambda side, one of the key benefits of serverless, in particular AWS Lambda, is it automatically scales based on your usage. So as I mentioned earlier, if you were doing queue-based processing and there was not a message in the queue, there's no need to long poll. The Lambda service itself takes care of checking that queue for you and only invokes your function whenever there is something to do. Similarly, if you have an API that's powered by Lambda via a service such as API Gateway or AWS AppSync, Lambda will scale out only as requests come in and invocations come into the API. And the way this works is, as requests come in, Lambda will concurrently spin up different execution environments for your code. It'll pull your code down from S3, it'll initialize any of your code that's outside of the handler, and then enter your handler for each of these concurrent executions. But when it finishes executing your code, it doesn't just dispose of the execution environment it just spun up. It actually will keep that environment around for a period of time, and if you invoke the same code again, the same function again, externally coming in from the same event source, then we'll effectively jump directly into the handler and reuse that execution environment. Now, the key thing to know here is concurrency is the unit of scaling. So with Lambda, there is a default concurrency quota on your account per region. And you can certainly exceed that, but you do want to request a limit increase if you need to go above that limit. And you can actually go in the new service quota dashboard and see this limit for your account in the region you're running Lambda. There's an additional quota set around your burst capacity. So what I mean by burst is if you go from no invocations of a Lambda function to all of a sudden having a fire sale, and in the same few seconds, you go from 0 to 10,000 requests per second. That would be the burst. And it's really about how many concurrent invocations did you spin up in a given minute of time. And so there is a burst limit. That is a limit that is not a limit you request to change. It's published as kind of a static limit set per region out on the Lambda documentation. And you do want to be mindful of this limit because if you do have an event coming where you do know you need to have, for example, beyond the 3,000 concurrent executions available in the first minute, which would be the default quota for, say, the Oregon region in the United States, you can still accomplish and satisfy that fire sale event, but you may want to pre-warm out the Lambda execution environments in advance of that event to ensure you don't have any throttling that would occur from it exceeding the burst limit in the first minute. And the way the burst limit works, there is a quota for the first minute of burst, and then for the capacity that's added every minute following until you get to the peak request concurrency that you're seeking. So as I mentioned, it is possible to pre-warm your functions to ensure they're scaled out in advance of a large traffic burst, and to even keep them scaled out if you know more traffic is coming or you want to just keep the function scaled out for some other reason. The nice thing here, though, with Lambda, from a reliability perspective, is that all event source retries, depending on the integration, if it's an asynchronous invocation in particular, so coming from S3 or SNS or SQS, all of those would be automatically retried by the Lambda service. At the same time, if you're doing a stream-based processing workload where you're using Lambda, maybe reading a Kinesis stream or a DynamoDB stream, we also would automatically retry reading events from the stream, and the Lambda service will automatically checkpoint where you are in reading the stream and take care of that for you. So scalability and reliability are both baked into the Lambda service by default. And next we'll look at security, and we'll start with containers.
So when it comes to container security, Fargate is an attractive option because each Fargate task runs in an isolated environment. There's no shared kernel or shared memory or shared CPU. Each task is executed in an isolated environment with no other tasks. The only containers that are running within that environment are the containers that are part of the task. With Fargate, we also make use of what's known as a cross-account ENI. And by virtue of having an ENI, a Fargate task can participate in a security group. So you can use security groups to control network ingress and egress. Another really attractive option with Fargate is the ability to assign an IAM role to a task. So if you have an application that needs to fetch an object from an S3 bucket or write to, say, a DynamoDB table, rather than embedding your AWS access key and secret key in your code or fetching it from, say, Secrets Manager, you can simply add an IAM role to your task definition. For ECS and EKS tasks or pods that are run on EC2 instances, you have slightly fewer choices. With ECS tasks, you still have the ability of running your task in AWS VPC networking mode, which allows the task to acquire an ENI. And as I mentioned before, that ENI allows it to participate in security groups. But if you choose a different networking mode, like Bridge, for instance, then you're relegated to using security groups for all of the containers that run on that instance, which is not as fine-grained. For controlling or isolating traffic within a Kubernetes cluster, you would look at using Kubernetes network policies to do that. And today, the only officially sanctioned way to assign an IAM role to a task is through IAM roles for tasks. That capability is coming to EKS later this year, probably within the third quarter. In the meantime, customers can use open source projects like kube2IAM or KIAM. That's the way that they've been solving this for now.
So when we take a look at Lambda security, there's two key pieces to the security of your Lambda function. First is who or what can invoke the function. So we have a function invocation policy, which is a resource policy. It's about who can invoke this function. And then the other piece is what can the function do. So in this case, we have an execution role, which is an IAM role. It would have a trust policy of the Lambda service that you can assign to the function, which means at runtime, inside the execution environment, it's going to have this IAM security context. And what could the function access inside AWS? So with these two policies and roles together, the function really gets its permissions. But for more traditional use cases where you want to have network level permissions and boundaries as well, you also have the ability to attach your function to a VPC. Effectively, the way this works is your execution environment lives in a Lambda service, a Lambda maintained AWS account, and we can get an elastic network interface from your customer account and attach it cross account to your Lambda execution environment to get you into your VPC. Now that ENI that we've gotten, of course, like any ENI, has security groups, so you can use traditional security group controls with Lambda to make that possible, to refine the ingress and egress traffic for the function with that ENI. And finally, with Lambda, naturally with your code, you are accessing things that do require secrets at different times. So maybe you need to securely retrieve a database password to make a database connection, or you need to have an API key to make a third-party service call. Well, environmental variables, and particularly secrets, can be stored and managed using parameter store and or secrets manager. And so anything in secrets manager can actually be retrieved with the parameter store API, a simple API, get parameter, put parameter, that can be used to basically retrieve secrets at runtime and encrypt them at all times with KMS until they're needed in your code. So you have a variety of options here with Lambda as well. So next we'll take a look at performance, and we'll start with containers.
So from a performance standpoint, there are lots of different options available when it comes to configuring your Fargate tasks. You can create tasks up to 4 vCPUs and 30 gigabytes of RAM. With ECS and EKS, you have a broader set of options. You can choose from among instances that are GPU optimized or that are lower cost than Intel processors like ARM, for example, for when running web front ends. And you also have the ability to choose from among various purchasing options, from on-demand to reserved instances, as well as spot instances.
When it comes to Lambda performance, it is a simplified computing environment in terms of configuration. So there's only really one knob to dial here related to the memory allocation for the function. And this could be as low as 128 megabytes of RAM or as high as 3 gigabytes of RAM. And based on what you assign, we do allocate CPU and network resources proportionally to that. Now the key thing to know with Lambda is the longest runtime that your code can execute is 15 minutes. So if things go beyond 15 minutes as part of a larger workflow, it still may be possible to use exclusively Lambda, but you want to look at some asynchronous patterns of maybe triggering something and then having a callback pattern when appropriate, or maybe a distributed workflow with AWS Step Functions, which we'll describe more in depth shortly. And then finally, we'll take a look at cost optimization of the two services.
All right, when it comes to containers, if you're using EKS, you pay for a highly available dedicated control plane. It comes to about $140 to $150 a month. And in addition to that, you pay for the worker nodes. Now, the cost of the control plane doesn't change regardless of how large your cluster is. You can have a cluster that only has a handful of nodes or as many as 5,000. The cost doesn't change. For ECS, like I mentioned on the previous slide, there are different pricing models available. You don't pay for the control plane, but you do pay for the running instances, the instances that are used to run your containers. And there you can use, like I said, on-demand, reserved instances, as well as spot. With Fargate, we only offer on-demand billing today. We are looking at different introducing new cost models in the future. Today, there is a 1-minute billing minimum, and after that 1 minute, it is per second billing thereafter.
So with Lambda, the pricing is based on a combination of 2 dimensions, and it is all on-demand pricing. So the first is the number of requests, and the second dimension is the duration of compute time you use. So when I say duration, we calculate this in gigabyte seconds, and it's rounded to the nearest 100 milliseconds in time. So the way you can actually find out what was the memory that was used and what was the build duration is every time you run your function, these are written to CloudWatch logs, and you can actually monitor those. And so there's a neat project called Lambda Power Tuning that will help you automatically fine-tune and right-size, in effect, your Lambda functions by using our Step Functions orchestration service to run your function with different memory levels and dynamically read these logs to figure out which memory setting is the most optimal. Because one thing that may be less intuitive at first is increasing the memory on a function doesn't inherently mean that you've made it more expensive. Because by increasing the memory, the function may finish faster, and there is a break-even point of which point memory increases will result in cost savings. And so Lambda Power Tuning will help you find the most cost-optimized memory setting for your function. And then finally, I want to mention that Lambda does have a free tier of 1 million requests per month and 3.2 million seconds of compute time per month. So you can really use Lambda a long way before you would ever exceed the free tier. Now that we've taken a look at all of these different areas, I want to just summarize for you the various compute decision factors for your architectures. So to make these decisions easier, we've built a decision tree of the various factors in deciding between Lambda, containers, or using both in your workload. And the first decision to keep in mind is what level of management are you looking to kind of adhere to? Are you looking to manage your functionality at an application level, or are you looking for more of a platform level runtime? And if you know you need to have hybrid environments or on-premises portability of the workload that you're running, then for these use cases, you know right away you may want to look at something like Kubernetes and our EKS service. But for many customers, they take a serverless first strategy where they want to use Lambda, and only when Lambda is not a good fit do they look at something else. So in such a case, just to make sure Lambda is going to work well, there's a few other considerations. First, does the task, is it short running? Meaning, does it run for 15 minutes or less? Or if it's part of a broader workflow, each component of that workflow could run for 15 minutes or less. So things like step functions could allow you to run a workflow as long as a year. So with step functions and Lambda, this constraint would not really keep you from using Lambda. Additionally, Lambda runs on commodity hardware. So you have a max of 3 gigs of memory, and you don't have the ability today to use things like GPUs or ARM or other specialized hardware. So for these reasons, if you need that, you would need to look at containers or something else. And then additionally, you want to be conscious that Lambda is a stateless environment. So you have ephemeral temp storage, which you can read and write to throughout the function's lifecycle. And you also, of course, can read and write state from things like S3 or DynamoDB. But you don't have the ability to use something like real high I/O, IOP state local disk that you might have in other environments. So you just want to be conscious that anything you write to that temp storage will go away, and you need to be prepared to handle a stateless environment. And then finally, you want to be conscious of Lambda scaling behaviors and Lambda burst limits. So in the documentation per region, there is a burst limit for each region, which documents how far out you can go concurrency-wise in a given region. And even if you need to exceed that and you have a fire sale type event, you can certainly do so. You just would want to pre-warm the Lambda service and your Lambda functions to be scaled out in advance of such an event for a really high burst in traffic, like a concert sale. But for periodic day-to-day bursts, if you have unpredictable bursts, as long as it's within the burst limit, there's no issue. But if it goes above the burst limit and you can't predict it, then you could be throttled by the service. So you just want to be conscious of that. But all of these things mentioned, many customers find Lambda and the ability to focus on their business logic and ability to take advantage of the serverless capabilities very attractive. So for these reasons, they choose to follow a serverless first strategy. But for any use cases where you may also want to use containers, you want to be thoughtful about how to choose container solutions as well. And for these, I'll turn over to Jeremy to describe the differences.
Thanks, Justin. And as you mentioned earlier, if you require a hybrid environment where you have a consistent API to interact with both on-premises and in the cloud, that's where you would want to look at using EKS, because the Kubernetes API that we offer as part of EKS is no different than the API that you would run yourself if you were running Kubernetes in your own data center. If you had to run a legacy .NET application on Windows instances, Windows hosts, then your best option there would be to run that container, that Windows container, on ECS, because that is the only option we have that offers production support for running Windows containers. We do have a preview of Windows containers with EKS, and it's likely that we'll offer support for that service once version 1.14 of Kubernetes becomes generally available later this year. But until then, if you need to run Windows containers in production, then ECS is your best choice. If your workload requires a specialized hardware, for example, if you're running a machine learning algorithm or model training workload that can harness the power of a GPU instance, then ECS or EKS are good options because there you have the ability to choose the instance types that you use for your hosts. If your application is stateless, that is, you don't need to persist state or the data that you write to disk doesn't need to be needed beyond the life of a task, then Fargate is an ideal choice because there's no infrastructure for you to manage. Fargate does have storage available, but that storage is ephemeral. So once the task stops running, that storage is no longer available. So if you're, like I said, if your applications are stateless, then Fargate is a really good choice for that.
Now we mentioned the power of and. So these services are not mutually exclusive, and AWS offers a way not only just to use them for different components to make the best of breed in your architecture, but to also use them behind the same sort of services. So for example, if you are building a service that is hosted and powered by an application load balancer, an API, a RESTful API with Amazon API Gateway, or a GraphQL service powered by AWS AppSync, all three allow you to route differently behind the scenes to different types of services. So some routes could go to container tasks behind a load balancer, and some could go to Lambda functions for other routes, and combining the best of both in a single API or front-end interface. At the same time, maybe you have distributed workflows that need to do different things, and some of these activities may be long-running processes. For example, maybe you're training a machine learning model on containers. In that case, AWS Step Functions could actually allow you to orchestrate a full workflow. As you can see in this diagram, this is just a simple image processing use case, where it has native integrations with a variety of AWS services. And it could actually integrate and wait for the container task to finish, but still leverage Lambda for many other things in parallel, as well as just orchestrating the end-to-end flow with any business processes you may need to build out. And so that this natively for every single task that you visually build in your workflow can actually integrate with building blocks of the services here shown. So AWS Lambda, Amazon ECS, AWS Fargate, or even AWS Batch, which is also container-based. All 4 of these compute offerings can be integrated natively with AWS Step Functions. And with Step Functions, you never pay for waiting. So a workflow can last as long as 1 year if you needed a long-running business process to be executed. And in summary, we've shared with you today a variety of architectural considerations and pros and different strengths of each of the compute offerings we've mentioned. We hope that you've taken away something that you can use in your next application. We want you to realize it's not just Lambda or containers, but leveraging the strengths of each, if not leveraging both in the same workload. So thank you very much for your time today.